So I'm Krista Phelps with the Indiana Department of Transportation. I'm back to tell you about aggregate properties, and this is Module M2B. And we're going to look at how aggregates are classified based on their gradation and their physical properties. And then we're also going to talk about some special conditions to watch for and some of the things that you can do to prevent segregation. So first, aggregate properties. We're going to look at aggregate quality ratings, physical quality tests, general usage requirements, and gradation requirements. And so for fine and coarse ag, the definition, the Indiana state specification definition, fine aggregate should be a minimum of 100% passing the 3/8 inch sieve and a minimum of 80% passing the number 4 sieve. Coarse aggregate, of course, shall have a minimum of 20% retained on the number 4 sieve. So in terms of fine aggregate quality classifications, fine aggregates do not have a specific rating anymore. We've removed that from our paperwork. They used to have A and B ratings, but you won't see that now. So for requirements of fine aggregates in accordance with 90402 and the state specifications, this shows the type of construction and then what fine aggregate is acceptable for that type of construction. So in these circumstances, you would want to consult the spec book to find out what type of material might be used in certain applications. So in terms of fine aggregate requirements in Indiana, we look at bulk specific gravity and absorption, and we are doing some micro-Duval testing now for abrasion resistance. And then we look at soundness. We look at deleterious, which we talked about some of the deleterious materials, and special requirements on fine aggregate. And then some of the special requirements for fine aggregate include acid insoluble testing, fine aggregate angularity, and testing for organic impurities. And for coarse aggregates, in terms of quality classifications, coarse aggregates are assigned to quality classifications, and it's based on their physical quality properties, their graded size, and how the material will be used. So for coarse aggregate requirements, you would consult the spec book. 90403 is for coarse aggregates. And it defines the limits as far as the testing that we do on coarse ag for physical quality, and it also defines the gradation requirements for state specifications for coarse aggregate. And coarse aggregates are divided into classes based on these quality requirements. So these are the quality ratings for coarse aggregate. And basically you have A through G, which on this graphic, class AP should arguably be higher than A because it has that extra requirement, right, for concrete. We run class AP aggregate through rigorous freeze-thaw testing, 350 cycles of freeze and thaw. And that's how it gets that AP rating for concrete. And then the rest of the classifications are basically just based on physical qualities, and you can find those again in 90403. And then class G is material that's so bad that it's, not even really for NDOT use. So in terms of classes of coarse aggregate, in various types of construction. This chart shows the type of construction and then what is required. Again, you can find these in the state's standard specification book. And the minimum quality rating for specific uses, here you can see that, how that plays out. Again, you'd have to, for specific applications, you'd have to get in and into the spec book and read about the special requirements for each application. So in terms of aggregate for hot mix asphalt, there are requirements placed on the aggregate before it can be used for those applications. So it has to be strong, tough, and durable. Have the ability to be crushed into bulky particles. And then also low porosity, low permeability. And then you want the correct size particle for optimal pavement. So some of the properties that we test for, absorption and specific gravity, resistance to abrasion, soundness, and then other requirements as they come up. So the quality tests that we run on aggregate, on coarse aggregate, bulk specific gravity and absorption is T85. LA abrasion for durability and strength is T96. And then there's 3 soundness tests that we run. So we have soundness, freeze and thaw in water, T103, sodium sulfate, T104, and then brine is ITM 209. And for fine aggregate, the test method is T84. So this tells you the definition of absorption. So you have a particle, and the particle has a certain amount of pore space, and so the pores can absorb liquid, water, or in the case of asphalt, binder. So according to how much pore space the particle has, that will affect how much liquid the particle can take in. So aggregates with high absorption are not desirable in most applications. So the reason for that would be that the more pore space there is, the more binder that you would have to use, which, binder contains oil, and it can be fairly expensive to have materials that are absorptive. So while some of these aggregates might possess skid-resistant qualities, they would also place a demand on how much binder was needed. So this shows internal pore properties. You can see the graphic on the right. So absorption is the particle's ability to take in a liquid. Porosity is the ratio of the volume of the pores to the total volume of the particle. And then permeability is the particle's ability to let liquids flow through. So density and specific gravity. Density is the weight per unit of volume of a substance. So you can have 2 items that are roughly the same size, like a baseball and a tennis ball, and the baseball is much heavier than the tennis ball. In fact, if I was to pick up a baseball and launch it across the room at someone's head, it would hurt pretty badly if they were hit with it. But, a tennis ball, they might brush it off. They might not be as mad at me in that circumstance. So as you can see, they're about the same size, but the weight makes a big difference. So that is because of their density. And specific gravity is the ratio of the density of substance to the density of water. So again, it's the ratio of a weight of a substance to an equal volume of water. And this shows some common materials and how they compare with water. So if you've ever, stood at the bank of a stream and thrown a stick in and watched the stick float down the river, the reason why that might happen, instead of, say, for instance, a chunk of lead, would sink to the bottom of the river pretty quickly. The reason why is because of the specific gravity of that material. The wood is lighter. You can see 0.7 here on this chart, and lead or gold um, is considerably heavier than water, so it would sink very quickly. So you can see here, kind of how the different materials shake out, and some of the materials we see here: limestone 2.6, and steel slag 3.5. So all these materials have much different specific gravities. So specific gravity can be really important in terms of asphalt mixtures, because it affects how much cementing material is needed, and mixtures are designed using volumes, and specific gravities allow for the conversion between weight and volume. And so NDOT has a GSB list that comes out every year around this time of year, and we track the most recent values for specific gravity for materials, and then we also look at the history of that material, and try to come up with a good number, an average of maybe the last 5 years of how that material has tested, and then again, we publish it this time of year, and then contractors use those numbers to make their mix designs. And so this shows some of the equipment used for running bulk specific gravities, and you guys are going to learn more about that in the lab portion of this class throughout the week. And so for steel furnace slag, specification requirements are a little bit different. CAT producers producing or processing steel slag are required to establish controlled testing for bulk specific gravity at 1 per every 2,000 tons, establish a target bulk, and then maintain a 4-point moving average. And material produced outside of the control limits is to be isolated. The bulks are a little harder to pinpoint with steel slag, and so we have a little bit tighter controls on those. So resistance to abrasion is the aggregate's ability to resist destruction by mechanical means, and so rolling during the paving process, and then also when the material is under traffic conditions. So here you can see a picture of aggregate breakage because of the roller. And one of the tests that we run is T96, Los Angeles abrasion for coarse aggregate. And this shows the piece of equipment that we use. It's basically it's a big rock tumbler. So you have a revolving steel drum, and then the steel balls, you can see them in the pan off to the right-hand side of that piece of equipment. And then, we put the steel balls in there and with the aggregate and let it tumble around, and then see how much material is lost. Sieve it again when it comes out, sieve it when it goes in, sieve it when it comes out, and then see how much material is lost. And that tells us, how prone to breakage that material is. So this shows the steel ball going into the tumbler. And soundness is another thing that we measure for physical quality properties of an aggregate. And it basically measures the aggregate's ability to resist harsh conditions like what we're seeing this winter, where it's I think today is supposed to be in the 40s, and this weekend it's supposed to get down to like -3 or something like that. So, so we put our aggregate through freeze and thaw cycles, similar to what they would go through on Indiana roads. And then also, we have brine and sodium sulfate testing to kind of simulate exposure to salts, which, we saw our roads here. So, we want to make sure that the aggregate is going to hold up under the conditions that it goes through on our roads. So quality requirements for soundness for coarse aggregate may be found in 90403. I've said that a lot, so you guys should know where that's located by now in your standard specification book. So freeze and thaw in water is AASHTO method T103 again. And the material is, according to this test method, immersed in water and subjected to 50 cycles of freeze and thaw. And then, after completion of all the cycles, then we weigh the material again, and then we find out how much material has been lost. And then we can see how the material holds up under freeze thaw conditions. So sodium sulfate, AASHTO method T104, and it doesn't involve any freezing. It's just the material is immersed in sodium sulfate solution for 16 hours and then dried to a constant weight. So then there's 5 different cycles. And then after completion, again, the material would be rinsed and dried to a constant weight. And then we would see how much material was lost on each sieve to determine how the material broke down throughout the testing. So this shows kind of, how we keep track of samples and how they're, put into the sample bags and marked and put into the freezer for freeze and thaw. And again, you see your size fractions here in the sample bags. So freeze and thaw in brine, similarly, ITM 209, the material is immersed in a brine solution and subjected to 25 cycles of freeze and thaw. And then after completion of the final cycle, rinsed and dried to a constant weight, and then calculated according to the sieve to see how much that material broke down during the testing. So we have at our disposal these 3 tests. We look at T103 the most, but then, again, we do have T104 and ITM 209 for sodium sulfate and brine testing. And, some materials we as a normal course, run those tests on instead of T103, but T103 is, generally speaking, the test that we use the most. Class AS requirements, the Class A for SMA stone matrix asphalt pavements. You see here highlighted in A, or highlighted in red. Oh, see? Class AS requirements. So you can see here, Class A for SMA stone matrix asphalt pavements. The quality requirements for this classification are the same as Class A, except for the LA abrasion requirement is a little tighter at 30%. And the testing is in accordance with ITM 220 and includes the micro Duval requirement. So other requirements in terms of deleterious or non-durable particles. So we've got soft material is determined by ITM 206, the brass rod scratch hardness test, and then known structurally weak materials. We talked about some of these materials in the last module. And then these tests are conducted on material retained on the 3/8 inch sieve, and then also visual identification of known non-durable particles. So this shows the scratch hardness tester. So you've got the little needle there at the bottom of this device where you can see what you would do is take your aggregate and push up slightly against that, and then if it makes a scratch, then you know that the material is soft enough to be scratched by this device. And also what you're seeing here is the setup for lightweight chert testing. And so in accordance with 90403, lightweight chert is limited to 3% in Class A applications. And we wouldn't test every sample for this. We would only test if the chert content was, above a certain amount. And so in terms of particle shape, you can see here in the pictures, you've got more of an angular shape there at the top left, and you've got a rounded, when gravel comes out of a stream, it's tossed around and rounded down into those smooth particles you see there on the right. And so then you also have crushed stone and gravel. So what you would see there on the top left would be more of a crushed look rather than a rounded look. And angular particles tend to interlock, creating stability, as you can imagine. And then you've got those particles there at the bottom, which would be considered flat and elongate. Our specification is that 10% of the particles may not have a length to thickness ratio of greater than 5. And dice-like particles that's the optimal shape we like to see. Okay, so in terms of special requirements, for coarse aggregate, again, flat and elongate, ASTM 4791 is the test method. The length to width ratio is 5:1. And for coarse aggregate angularity, ASTM 5821. And that test method is how you determine the number of fractured surfaces, one-phase crush versus two-phase crush. And so what this test method is showing here, uncompacted voids in fine aggregate, AASHTO T304. This test measured the angularity of fine aggregate. So we measure acid insolubility. For fine aggregates, there's a spec that the acid insoluble fraction will be no less than 40%. Can be found in 90402 again. And this specification applies only to fine ag used in 4.75 sand surface mixtures. So in terms of the surface texture of an aggregate, that plays a big role in surface mixtures. So the pattern and the relative roughness or smoothness of an aggregate particle, and this impacts how the aggregate would bond with cementing material. And so if there's a little bit of roughness to the particle, it gives that material something to grip. And surface texture polishing becomes a big deal over time. Aggregates may polish if they're exposed to traffic, which wouldn't be an issue for most vehicles if they are able to go and put new tires on their car when it's needed. But some people are living life on the edge, and their tires may be a little smooth, and put that smooth tire against a smooth surface, and then you may have a problem. And so for aggregate to be used in surface mixture, we require additional testing for polish resistance, and that, that's the reason for that. And that picture at the bottom kind of shows you, I guess, the differences between rough particles versus there on the right you have a particle that's very polished. So again, in order to become a polish-resistant aggregate, sources must undergo a series of specific tests. The ITM that describes the process is ITM 214, and it includes an initial test on a polishing wheel, and then from there, the source would get permission to test the material on a actual test strip on the road. And then the test strips are skidded against a control a few times per year, and then we take a look at the results and just make a determination on whether or not we can approve that material as a polish-resistant aggregate. And ITM 221 describes the process for polish-resistant aggregate with higher ESOL. So some of the special requirements for HMA aggregate, we have dolomite approved materials. The test method is ITM 205. Those materials are approved according to their magnesium content. And we have sandstone, which again, I think I mentioned earlier that it's kind of a rarity for a sandstone to be approved, but we do have some materials that come out of Southern Illinois that have been approved for use in surface mixtures. And then we have polish resistance, and the ITMs again are 214 and 221. And we have slag, and then also crushed materials, and those are determined in accordance with ASTM 5821. So this, as a review, this chart just shows you the test method associated with some of the physical quality tests that we run. So for general usage and gradation requirements, and again, you can find those for fine aggregate in 90402 and for coarse aggregate in 90403 of the state standard specification book. So additional gradation requirements. So for B-barrel structural backfill, you can find that in 211.02 of the standard specification book. And for riprap 90404, aggregate base 30102, subbase 30202, and aggregate pavement or shoulder 30302. And here's the Indiana specs for gradation for fine aggregate. Again, this chart can be found in 90402. And for coarse aggregate requirements, again, this can be found in 90403. And this shows the different coarse aggregate state specification products and the required gradations associated with those products. And then the footnotes down there at the bottom can be important to read through as well. For instance, on SC products, the footnote number 5, so it should be 85% one-faced and 80% two-faced crushed. And then there's flakiness requirements found in ITM 224. So, take a look at those as well, because sometimes you could find information in those footnotes. So one thing that's important, when the aggregate product leaves the cap producer, there is a certain gradation that product is at when it leaves. It either meets state specification or it meets gradation requirements for a QA product from that source, according to their QCP, according to what they're approved for. And so it's important that the aggregate is handled in such a way that we don't cause segregation or degradation of that material to occur after it leaves the cap producer. And so that's why we're kind of, I guess, adding this to the presentation to just, things to keep in mind, at the plant in stockpiling and handling the material, because every time the material is handled, you can cause gradation problems with that material. So this shows some of the different scenarios where segregation and degradation can occur. So you have conveyor belt segregation. As the material moves across the belt, it bounces up and down. You can have materials segregating according to their weight, according to their size, based on that movement. And at the end of the belt, if left undeflected, so there's like a panel that you can put there to deflect the materials to keep them from segregating as much. But if that is not done, fine particles would drop closer to the belt, and then coarse, or the more coarse the particle, the farther away from the belt it would drop. And also another factor that can weigh in is the height of the conveyor drop. So the higher the drop, the more segregation you're going to end up with. And then also degradation can occur because when that material hits the pile, the higher you drop it from, the more impact you're going to have. And then you can see here in this picture the fines blowing off there to the right, off the material that's coming out. So you're losing some of the fines in that material. So within a stockpile, you can get segregation due to gravity, and segregation is a big nemesis of stockpile and handling, but you can have other situations too. Degradation and contamination affect quality as well. So here you're seeing roll down segregation. So you've got the coarse, you got probably like a dense grade situation here where you've got the fines that are sticking to the center of the pile, and then you have the coarse aggregate running down the side. So there's techniques you can use to reduce that segregation. Truck-built stockpiles, and in one dump situations can reduce roll-down segregation. Requires a larger area, and to reduce the required area, you can restock some dumps on top of other dumps with a front-end loader. So this concludes this module. Hopefully you've learned a few things through this presentation about aggregate properties, and they help you in your class this week, and then also in your work lives. Thank you, and you rock.